Today we're presenting the insights and experiences had while teaching a large-scale functional programming course at university. So we make a big jump from elementary school to university, where we already have brainwashed people. But in the future, maybe we don't have to deal with those anymore. Let's see. Anyway, this joint work with Jonas, but he's not here today, at TU Munich has said we ran the course twice, once in 2019 in physical space, and once in 2020 in virtual space due to the pandemic, as you know. All right, so today I'm going to talk a little bit at first about the challenges and what kind of challenges do we have when teaching functional programming at universities. So number one is the number of computer science students just globally exploded, as you probably know, which is very nice for employers because there are many people to hire, but it's really difficult for universities because, for example, at our university, in just 10 years, the number of students more than doubled from just below 4,000 computer science students to more than 8,000, so 132% increase, whereas the number of academic staff that has to do all the teaching just increased by 31%. So there's an ever bigger gap, which is not good for us. And moreover, it also means that 1,000 plus students is just normal, for example, at our department for mandatory courses in particular. And luckily enough, functional programming is a mandatory course at TU Munich. So everyone gets to experience some Haskell and OCaml. But it also meant that Lukas, I, and Jonas, we had to teach 1,000 students somehow. All right, challenge number two, we had this radical transition to online classes. So in our first iteration, as said, we had the beautiful physical space. We knew how to interact with students. Students knew how to interact with each other because at the end of the day, it should not just be academic, but also a joy to learn something new at university. But in 2020, we had to move to this space. And it was very open how to do this, and in particular, we didn't want to get into this state where our students are just socially isolated, depressed, and not only hate functional programming, but also hate their lives. But we wanted to give them both functional programming and joy back to life, basically. Okay, and then number three, students question the usefulness of functional programming beyond academia. Probably you have heard that before. We got that feedback many times by university students because, well, I already know how to code in Java. Why do I need to learn about type classes and Haskell? And no one uses it in industry, right? So we think this is not just something which is prevalent at our university, but there is at least some evidence that some programmers online as well think that functional programming is a little bit odd. So we have to change that and get the community back to functional programming and not imperative programming. All right, so today the message is there is hope. We managed to cope with all these challenges, and we share our insights, our tools, and whatnot on our GitHub. So if you're an educator, check it out, because it's a lot of work to think about how to cope with all these challenges and to create all the exercises and mechanisms to keep everything running. All right, so while you're doing that, note that we used Haskell, but many mechanisms described in particular in the paper, which is also on the GitHub, apply to functional programming education and maybe programming education in general. All right, so today we focus mostly on the practical part. If you're interested in the lectures, in the theory, how we did that, then go on and read the paper. In particular, I start with some of the engagement mechanisms that we employed, and there are more in the paper. So again, if you're an educator, please check out the repository. All right, number one, feedback must come fast. So that's not something that we just invented and made up, but pedagogical research, proved that many times that students are more engaged the quicker they get a response by some system or by the educators and whatnot. So you really have to get feedback to the student very fast. And also, we, of course, did not just adhere to that principle because we're very nice teachers, but it was necessary to give quick feedback because we had to automate everything. There was no, there was no chance we could grade 1,000 submissions every week. So we had to automate everything. And what do you need to, run a course and automate everything in functional programming? For example, you need something that runs the test and manages the scores and so on. We used Artemis for this purpose. It's a tool developed at our university. It's free software, open source. If you're interested, chat with us later on. You can also run exams, which is quite interesting on that platform. You can run them digitally, and you can grade them digitally as well, which was really helpful for us to scale everything because you can write tests. The code gets tested automatically. You don't need to check everything if it already passes the test, for example. All right, then we use Tasty, which is some libraries for Haskell. Tasty, which combines quick check tests, small check tests, and date unit tests there's an emphasis in quick check because quick check was really the main driving horse here. We had to, of course, write our own generators, but the combinators by the quick check library make everything really smooth. So if you're a Haskell educator, you can, test everything you want to test from basic student submissions using these libraries. And moreover, we used HLint for stylistic feedback, and there's a story behind it, but you can ask us later on if you're interested why we used HLint and made it actually mandatory that students use HLint. But at the end of the day, they actually really liked HLint. They got immediate feedback about their code. They weren't annoyed, like, what is that squiggly line? Why is it red? I mean, it's correct, no? But they actually were really interested. Oh, I can fuse those map calls into one map call. Oh, it's still correct, nice. And it's like, oh, why is it yellow? Oh, I shouldn't say if true, then false, else true. I should say not X, for example, or something like that. And they were really, again, open to those suggestions. And finally, our lecture was not just about functional programming, but also verification of functional programs. And we also had to automate those kind of proofs, for example, for functional programs. And we developed a tool at our chair called Check Your Proof that is capable of checking some proofs about Haskell programs. So here's an example how such a proof would look like. So this is C by P syntax. Students can prove, for example, that the append operator on list is associative. There's some background definition how the append operator is defined. And then students need to specify how they prove it. So for example, here by induction on the list, on the first list XS. Then as a next step, they need to say, right, I have two cases. I have the empty case, I have the cont case. For each of the cases, they need to specify the goal they have to prove. And in the inductive steps, of course, they have to tell us, well, what's the inductive hypothesis? Okay, so they need to be really formally correct. And then at the end of the day, every subproof, every final proof in the cases is an equation of proof. So they just have to rewrite from the left to the right side using the unfolding of definitions or the inductive hypothesis, or for example, referring to a lemma they proved previously. And all this is automatically, again, checked. So it is integrated in in Tasty. So students have homework, submit a proof, get immediate feedback. We have no grading work. Again, if you're interested in this, let us know later. So that about the feedback. Now, number two, as already said, students don't believe us that functional programming can be practical. And obviously, it doesn't really help if we tell them, well, actually, do you guys believe it or not? But there's Lambda days and there are people using it. So we actually had to get those people into our course. So in 2020, we had a cooperation with industry partners and we had 3 workshops about advanced concepts, which are usually not part of the curriculum. And then, to our, not surprise, but to our delight, it was a great success. We had more registrations than we had spots available. And in some cases, students were so excited, like the workshop extended for multiple hours. So instead of like 3, it was like 6 or something. And the people that did the workshops were also super excited to get in touch with students and see like new functional programmers and tell them something about their hobby projects or the work they do at work. So it was a really, really great success. And today I want to make I beg you, basically, please consider doing the same if you're from industry. Contact not just our university, but contact your local university if you know they're functional programming educators and tell them, hey, I have like a side project or we have like projects at work. We could do a workshop about, I don't know, functional reactive programming or advanced I/O concepts. And then students really get to see, oh, there are people out there using it, and they will be much more interested in the course material. And at the end of the day, it's also, beneficial for you as an employer because you have more, people to hire at the end of the day. All right, and then finally, you should offer diverse challenges, and that's because students, we have different, means of how to approach certain problems. They want to solve different puzzles, and for example, in our case, we did that by offering diverse weekly competition exercises, which we also make available in the GitHub repository. There were a lot of work to create, so please, again, if you're interested in running some of those, check out our repository. Some of the examples, we created a game framework where students could play a game, they write a strategy, and again, feedback about such a game must come quickly, so once they submitted their strategy, it gets immediately executed in our server, it gets simulated against all other student submissions, and then they can go on the website a minute later and they see, all the games they played against all their peers. They can see some statistics. They can even replay the game in the UI. So it was really, really engaging, and students spent like too much time on it, basically, at the end of the day for what they got as homework points. And we also had a small framework to run ICPC-like contests. It's really lightweight, and if you want to just run programming contests, solve as many challenges as you can in like 3 hours, there's a small framework we provide in the repository where you can like have support for team names and some statistics and websites and so on. And finally, also some creativity. We, for example, have an exercise about creating a music synthesizer in the repository. And actually, one student really managed to create a really interesting tune with that. We thought it's a toy example, but yeah, they made some really good jingles. And finally, we also have the creative task where we tell students, right, just use some bitmap library or whatever you want and create some piece of art at the end of the day. It's like one of the final exercises. It's a bit more lighthearted. And this is one of my favorite submissions. A student created the Quine, that is a program that outputs its own source code. But he didn't output it on the terminal, but he created a bitmap of its own source code, which was quite intriguing to me. All right. I can say that it works really well to motivate talented students, those exercises, and to keep also people from different backgrounds engaged. There were some students that were really into music and they got more involved with the synthesizer, or the students were more into logical programs. So please keep it diverse and use our exercise if you want to. We also had an award for the top 30 students to keep it more exciting. And again, another plea, maybe consider either, offering some awards for students, or also, which would be even better if you're from industry, maybe you have some challenges. You thought like, oh, this is like a neat problem, or you as a person on your spare time, you thought about a neat problem, and you think, oh, this is a really nice competition maybe for students. Contact your university. I'm pretty sure they would be very excited if they get people from industry to propose problems to work on, and then again, students get a feedback loop, oh, there are people from industry that actually use functional programs, and they're getting more excited again. Okay. So that's about the engagement for today. There's more in our paper, but as of now, I pass on to Lukas, and he tells you a little bit about some technical issues we had to face.
Is it on? Yeah. Okay. Yeah. Right. So. We will just show one basically technical part that we did to test our students' code, because we thought that it may be interesting for people in industry especially. And this is about I/O mocking. So basically what the challenge that we are facing is that we want to test the submissions of our students with quick check automatically, and then I/O is an important part of the syllabus, so we are faced with the challenge on how do we even test I/O in Haskell. And I will now show you first basically the standard way to do that, which is also done. So this is how it would be done by frameworks such as hmock and monadmock. So first of all, let's consider a simple operation such as a copy file operation. It takes two file paths and copies the file from the file path given by the first argument to the file path given by the second argument, and of course this all happens in the I/O monad. And now what we do is we extract basically the side effects that this operation needs into its own type class. So this is now this monad file system M, and we replace the I/O thing by this M here. And then we implement the class as follows. So for copying a file, we just basically need two operations, and this is a read file and a write file. And then this whole thing consists of these two operations. And now we can implement the copy file operation quite straightforwardly. So we just read the file from the source, then we get the content, and then we write the file to the target. So that's quite simple. And now what we can do is that type classes allow us to do multiple instantiations, and then we can do one like trivial instantiation to execute this operation in the context of just the I/O monad. So this is trivial. But what we also can do is we can do a mocked version. So this is just an example how you could do it. So we define a mock file system, which is just a map from file paths to strings. And then we do an instance for this monad file system where we use a state monad to make it possible to modify the file system and then like read file and write file. I will not show the implementation here, but it's quite simple. You just modify the state of the file system. And then if you want to test something, you just check whether after the operation occurred, the file system is in the state that you expected given the state that it had before. So this is how you could do, you could test I/O in Haskell. But now, what is the problem with this? So why didn't we use this approach? The problem is that it lacks transparency. So for our students, what would happen if we use this approach is that they either would need to import this new type class or they have it in their file already. And this is problematic, especially because in our syllabus, I/O is introduced without talking about monads at all in the beginning, so that people get like started quickly with I/O. This is also what Hudak does in his book, I think. And that they don't think like that functional program is just a glorified calculator, so you can really do I/O, and we want to teach them this early, so we don't want to bother them with these kind of monads. So the solution is we delay this mocking to the compilation stage by replacing the I/O module with a mix-in, and fortunately Cabal allows us to do this. So basically what we are doing is, at compilation, we replace the whole I/O module by our own mocked I/O module. So, and how we do this is we have like basically a representation of the real world, and the real world, of course, consists of things like the current working directory, all the files in the file system, the handles like standard out and standard in, and all that kind of stuff. And there could be even more like the network, and I don't know what the state of the random generator, and yeah, it goes on for a bit, so that you can basically completely transparently mock the whole I/O monad. And then we have like one basically special thing, and this is the user, and the user is responsible for generating the input for the student code and reading the student code's output, and then like dealing with that accordingly. And then basically this is the state of the real world, and then the mocked I/O type is just, we put that again, like we saw previously, we wrap that with a state monad so that we can modify the real world. Then we wrap that with a pause monad transformer. I will come to that shortly, and then just around that we have an exception transformer that just adds I/O exceptions. So this is quite simple, this part, and now I will shortly give a glimpse on what this is. So this is the pause monad transformer, and basically it's a monad transformer for this pause monad. I will not go into the implementation, but just give you an intuition what it does. So it has two operations, a pause operation and a step operation. And the idea is what happens if you have basically a computation in this monad and you want to execute it, then you get back another computation in this monad, and then you get either the rest of the computation, and this happens if you encounter a pause, basically. Then it runs until you encounter the pause, and then it returns the rest of the computation after the pause, or it runs to completion, and then you just get back a value. And now, here is like basically what the purpose of this monad now is that you can model blocking operations. So here we have a very simple example for a student submission that just reads some name and then outputs hi and the name, and the mock user just tests whether if it just reads the output, so it puts in some name S, and then it reads the output, and then here this is omitted, but it checks whether this matches the expectation, basically, and if it doesn't match this, then it fails, and then the test fails, basically. So the user is also the test. And then we have, so if we step through this program, then we get to this get line, and now what happens like in the real world is that this get line blocks, right? It waits for a user input, and this is and here the pause monad comes into play because this corresponds to a pause, and then basically the whole framework, what it does is it encounters this pause, and then it switches over to the mock user and now executes the mock user until that one is paused in turn. So what we do first is we put this name to the standard in of the student, and then we want to get the output of the student, and then this blocks again, and now we switch back. Then here we get something because we put it here, then we output it, then the computation finishes, and then we get here. So since we have put something here, we can read it here, then compare it, check whether that's correct, and then this is basically the whole test. Right, and that's basically how we can test I/O. Right, if you have further questions, you can ask them after the talk, I guess. Yeah, find more in our repository. Kevin already told you this repeatedly. And then if you have any questions, you can ask them.
So we'll do the following things concurrently. Frederick will start setting up. We have time for a question while he's setting up. And we'll do the evaluation of the talk. So let's do all of that in 1 minute or less. So any questions while the next speaker is setting up?
So yeah, one of the things that that you mentioned was that the students already have this ingrained like imperative programming in their minds. So, and this is something we found too, is actually sometimes it's harder to teach the first year's Elm than it is to teach like the 9-year-olds. So what do you think that the big problem is that so I guess, what is your experience? Why do you think that is? And sort of, do you think it's this idea of them being sort of so ingrained that it's hard for them to learn the new concepts, or what's your sort of take on that?
So you're asking why they stick to the imperative world, basically?
Yeah, I guess so.
It's hard to leave the imperative.
Yeah, why do they find it hard to leave that? Yeah, what do you think?
Do you have a good answer?
I find it difficult to say, but I think like apparently this functional thing is just so much different that they really miss the features that they get from imperative programming, and they think like functional programming is complicated. But yeah, it's also our experience that if you teach them functional programming first, then they don't find it difficult at all. It's just way more natural, basically. But yeah, I'm not really sure why that is. Yeah, I think just at the paradigm set.
I think also one of the problems is that students, I think once you understand that many problems in computer science just boil down to, well, make the problem smaller and solve the easy cases, put it back together, I think it's easier to do functional programming because many times you're just doing recursion in a data type. But people in university, it's easier to say, I want to add a number, I want to store something, I want to read something. It's like to think like step by step rather than, break it down and then solve easy cases. It's more like mechanical thinking rather than compositional and abstract thinking. But I think, so it's not very, I really wonder that, I'm really surprised that it works so well for kids actually. I thought like it should be nicer. I think it's, once students get like basic introduction to fundamental programs and then learn about divide and conquer and stuff like that, it should be easier to functional program, but I don't know, there's like a big gap between this is like an algorithm and this is functional programming, but it's actually the same thing, break it down and then put it back together.
Oops. Thank you very much. Right.